So this data set that I mentioned earlier of temperatures in all 82 counties of Michigan going back to the 1890s is pretty big. And any data set that you deal with is going to be a little bit of a challenge once you get beyond a relative handful of observations. So our goal is going to be to try and summarize it and look for characteristics. Now there's a couple different types of characteristics that we're going to be looking for. We're going to look to try and find what typifies your data. What do I mean by that? Something that's representative in terms of the mean, or what's called the median, which is going to separate the top half of your data from the bottom half. The mode, what's most frequent about it. You can also look at the mid-range. Once you know what's typical, then it's easy to decide what's atypical. What are the outliers? In fact, there's a book on outliers. It talks about guys like Isaac Newton, geniuses. Why are they so far out there? Another thing we're going to want to look for is the distribution, the pattern of data, how spread out it is or how clustered it is. What's its shape when you graph it? Are there changes over time? So there's a lot of different characteristics, but it all starts with summarizing your data in some way, and that's what we're going to pick up with in section 2.2 is summarizing your data. Let me flip open to problem number 6. And actually, I'm going to copy this down here. We've got an age in years. When an actor was chosen to win the best age in years of best actor when Oscar was won. So age in years, these are people who won an Oscar, and the frequency. And I'm going to use this example to define a lot of terms. So 20 to 29-year-olds, there was one person in this age range who won an Oscar. 30 to 39 years old, 26 of them. 40 to 49 years old, 35 of them. 50 to 59 years old, 13 of them. 60 to 69, 6 of them. And 70 to 79, 1 of them. Okay, so some definitions regarding this stuff. What is it all saying? In particular, how we discuss it. So the first thing I want to point out and give a name to is these numbers that help define our different classes. These ones are called the lower class limit. So lower class limit. By contrast, then, what do you think this one number would be? This set of numbers would be called? Yeah, the upper class limit. And then you can get the class width, how wide these are, by subtracting adjacent upper or lower class limits. So if I subtract these two, then I get a class width equal to 10. Now there's something else that is kind of hidden in working with data like this, and that is, well, what separates this class from the next class? At what point does somebody land in here as opposed to let somebody land in here? If you notice, there's a little bit of a gap. What happens to somebody that's 29 and a half years old? What class do they go into? So those kind of hidden values are called the class boundaries. So class boundaries. And given that, your data consists of ages, are you going to round up? Are you going to round down? It's kind of up to you where you want to put these class boundaries. But the class boundaries in this case would be the midpoint of these two. So 29.5, 39.5, etc. 49.5 all the way up to 69.5. So class boundaries are the numbers used to separate the classes, but without the gaps created by the class limits. Now, one thing that is going to be a little bit of a challenge, not much of a challenge for us, is that some of the software that we're going to use deals with these issues differently. As near as I can tell, Google Sheets, if you had something like this, you would be including the 29, whereas StatDisk seems to put that 29 or couldn't put that 29 in a different category. It's something we'll have to pay attention to. Let's try another one like this, just to try and give you a chance to see that you understand some of these ideas in terms of class width, lower class and upper class limits, and class boundaries. So it's the same idea, it's just a different data set. It's problem number 8, and I'll copy that down for us here. So it says years. I'm not going to write it all down. Years the president lived after first inauguration. So years lived. 0 to 4, and then the frequency. And then 5 to 9, 10 to 14, 15 to 19, 20 to 24, 25 to 29, and I think this last one has to be Jimmy Carter. We've got to go all the way down to 35 to 39. We've got 8, 2, 5, 7, 4, 6, 0, and 1. So what I want you to do is find the class width, and the class boundaries. And we'll also throw in something else that I haven't defined yet, but maybe you can kind of figure it out. The class midpoints. So while you work on that for a minute, I'm going to walk around and just kind of get your names checked in a little bit, at least in my mind. So if you're watching this at home, you can fast forward until I take the pause sign off here. So if you would, I know I just collected or went through the attendance, and if you would, just tell me the name you'd like to be addressed as. finish this up. This. Okay. So, how wide are these? How wide are the classes? Yeah, 5 years. All right. So, if you take any adjacent to upper class or lower class limits, the distance is 5. So the class width is 5. How about the class boundaries? Where are these? What's kind of the cut point for these? You know, from one category to the next. Yeah, the 0.5. Now, technically, and although you know it's not a real practical significance, technically it would start at negative 0.5 would be your first one, and then the next one would be 4.5, and then 9.5, etc. 14.5, all the way through 19.5, and I hope I don't run out of room. 29.5, 34.5, and one last one of 39.5. So those would be your class boundaries. Those would be, you know, what really divides one class from the next. Now, I hadn't discussed it yet, but I'm hoping that it might be clear just based on the wording. What's the class midpoint for this first interval? 2. Yeah, 2, and then 7, etc. It's just the average of these two values. Now, a lot of times this is handy because as you do things on a computer or something like that, it's nice to have your x-axis labeled, so you'll use the class midpoint for that. So just keep on adding 5, 12, 17, 22, 27, 32, and 37 would be your class midpoints. Nice. Nice. All right, let's see if we can't get our hands on some actual data. Are we okay with these first two examples? Just trying to give you some definitions there. All right. Now, in addition to the frequencies, sometimes what you can do is look at the relative frequencies, that is, turn these into a percentage. And what you would do there is figure out how many items are in your sample, and then divide each of these by that number and make them percentages. So, what? 10, 22, 32, 33. All right, so 33 in our sample. If you divide this by 33 and multiply by 100, you're turning that into percentages. So it's a different way to kind of address the same thing, trying to understand where your data is. Does there look like there's anything that's typical about this? Yes and no. I mean, this one's the most frequent one, but they're kind of evenly distributed except for this one, this category. So if you make it beyond 9 years, okay, that's good. You know, or if you make it to 4 years, there's a good chance you'll make it beyond 9 years, I guess is what this is saying. Let's look at the data from our little experiment here. And I'm going to do this in StatDisk. Where'd that sheet go? All right. So if you guys have downloaded StatDisk and you want to play along, that's great. But I want to just try and get at a conclusion here. Let's take a look at the frequency of our numbers here. So just 6, 0, 6, 2, 6, 2, 9, 5, 5, 3, 7, 7, 7, 2, 0, 5, 7, 5, 6, 7, 8, 6, 9, 7, 8, 5, 5, and 4. Okay, let's see if we can't find out some statistics about our data. And I might be jumping ahead a little bit. That's all right. I'm going to do a histogram. Now I'm going to define the class width as 1, starting at 0. And let's see what happens when we do that. There's just a bit of 1. Thank you. So let's graph it. So there's our data. Now, I'm not sure exactly what I expected, but let's see, there's a fair number of 7s here in the data. A lot of 7s and a lot of 5s. So a lot of 5s, not too many 0s. What I kind of expected was a lot of people would be saying something that ended in a 0 or a 5. Now what would that reflect? If people had a tendency to answer that they had a 0 or a 5 as part of their weight. Yeah, just kind of estimating. So you're rounding it up. So either a lot of you are paying really, really close attention to it, or maybe you're good at making up numbers, because this looks somewhat random. And we'll look more at that when we look closer at frequency distributions in the next section. But for now, yeah, it looks somewhat random. Not uniformly random, but random enough. One of the things we look for in our data is a nice shape called the normal distribution. Now, has anyone ever heard of the normal distribution or of the bell curve? What's the bell curve? Where do you hear about the bell curve? So a lot of times, a lot of natural phenomenon has this kind of a bell shape, a normal distribution. So normal distribution. And what this represents is the frequency of your data. That is, there's a tendency for a lot of your data to be close to the middle, and then as you move farther away from the middle, farther away from the mean, that the amount of data kind of trails off. So you'll have roughly 2/3 of your data is within a certain distance of the middle, and then maybe about 95% is a certain distance more. And then you get the outliers, stuff that's far away from your center. It's nice when we have a normal distribution because we know a lot about the normal distribution. So one of the things we're going to be working on is trying to understand, when do we have this kind of a normal shape? One of the things that says you don't have this normal shape is if you have a lot of outliers, a lot of stuff that's way, way out there. Intelligence is supposed to have a normal distribution with a standard deviation, with a mean of 100 and something called a standard deviation of 10 or 15, depending on the study. What that means is that people like Marilyn Vos Savant, sometimes considered one of the smartest people in the world, she's way out there. She's an IQ of around 200. That's way, way out there. That's definitely an outlier. Very extreme compared to what we're typically going to see in this kind of a distribution. If you have more than one outlier in this class, then the distribution you're dealing with is not a normal distribution. There's other ways you can decide whether or not something is normal. Taking a look at its graph is going to be our best way. Let's do a problem from the book. It actually inspired the problem that I gave us, which was to look at our own weights and deal with those. I expected a much different result in looking at things. Maybe we just kind of look at this and see the result I expected. So it says, weights of respondents were recorded as part of the California Health Interview Survey. The last digits of weights from 50 randomly selected respondents are listed below. What do you see in this data set that kind of stands out a little bit? Yeah, a lot of zeros and fives. In particular, if you did a frequency distribution, it looks something like this. You have 26 people that answered with the last digit of 0, and 12 that answered with the last digit of 5, and the rest, you only had a relative handful in between. So what that's suggesting is that people really didn't know. They're just kind of estimating. And you tend to estimate in round numbers. Let's look back at a couple of our problems in this section. Do you think that data like this could represent, if you graphed it, would it have maybe a bell shape? Yeah, it doesn't look too bad. You've got a pileup of data in the center, and then as you move away from the center in either direction, it kind of trails off. It's certainly better to look at this on a graph as opposed to just dealing with it in terms of its frequencies. But looking at this, I wouldn't say no out of hand. It definitely looks like it could be coming from a normal distribution. How about this one? Does this one look like it could be a normal data set? No. You don't have a big pile up in the center. It's not trailing off really well to either direction, so this one's definitely not normal. Tough to say exactly what it is, but it's not a normal distribution. Normal distribution can be a big part of our work in this class. Try and understand when we have it, etc. One of the nice things about your author's program, StatDisk, is that it has a built-in test for normal distributions. Okay. Let's in terms of frequencies, there's one last thing we're going to do with this. And it's construct a cumulative frequency. So let me look at the responses for problem number 20, and I've already summarized this for you, so let me write that down here. Last digit, this is of their weight. And we had a bunch of different responses, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then the frequency, 26, 1, 1, 2, 2, 12, 1, 0, 4, and 1. Those are your frequencies. Now sometimes, depending on the application, you want what are called the cumulative frequencies. So cumulative frequencies. So again, the first one would be 26, but then the second one, you're looking for anything that was 1 or less. So it would be 26 plus 1 would be 27, and then 28, and 30, and 32. So what you're doing is you're adding up the number of people that have a last digit in their weight of 4 or less. So that'd be 32, and then you jump up to 44, 45, 45 again, 49, and 50. So by the time you get there, you've got everybody. Now the fact that you've got 50 people in here makes the next part of this arithmetic very, very easy. If you've got 50 people and 26 of them have a weight in the last digit of their weight was a 0, well, 26 divided by 50 gives you 52%. So you can do the relative frequency. Relative frequency. So going back to this number, if you divide this by 50 and multiply by 100, you get 52%. One person represents 2% of the data. 4%, 4%, 24%, 2%, 0, 8%, and 2% again. Now, up to a little bit of a rounding error, this should total up to 100%. But, like I said, there is a little bit of rounding error there from time to time, so it may not be exactly 100%. That's okay. Just to make sure I'm clear about where this number is coming from, you take the total, which is your 50, divide that into your frequency, so 26 divided by 50 times 100, that's what gives you your 52%. And you would have to do that for each one of these. You divide the frequency by the count, and then multiply by 100%. For homework in this section, try 1 through 19. Homework in this section starts on page 51.